Are you making this common RF mistake? Hello everyone, let's explore the difference between return loss and the scattering parameter S11. We will visualize a propagating wave and its reflection, highlighting why measuring S11 is essential. Then we'll analyze an antenna's return loss performance using ANSYS HFSS. If you are interested in RF topics like RF circuit and antenna design, ANSYS HFSS simulations, or software-defined radio, please consider subscribing. I'll have more information coming soon. If you have been using the term return loss incorrectly, then you are in good company, as an IEEE editor-in-chief once stated that about 1/3 of folks who are supposed to know what they are doing have been getting it wrong, proving once again that RF is mostly black magic anyway. Before diving into the difference, let's briefly lay a foundation of what they are and why we care about them in the first place. A propagating electromagnetic wave has certain properties, including reflectivity. For example, have you ever wondered how light travels millions of miles from the sun, hits a windshield, and then suddenly redirects into your eyes? What caused the change in direction? The short answer is, it encountered a boundary. In this case, the boundary was glass. Free space has an impedance of approximately 377 ohms, whereas glass has, well, not 377 ohms. Voltage waves are complex quantities, as they have both magnitude and phase. To help visualize this, I wrote some code demonstrating a propagating wave encountering a boundary with a reflection coefficient of 0.5. The incident wave has an amplitude of 1 volt. Since gamma is plus 0.5, half of the wave reflects, and since our boundary here is not lossy, the remaining half continues through the boundary. It is a topic of another video, but I would be remiss not to at least mention that the reflected wave will add with the incident wave, resulting in a standing wave. This leads to some really cool RF magic where an open circuit will appear as a short and vice versa based on the distance from the boundary. Now imagine this wave traveling through a coaxial cable and hitting a boundary at port 1 of a network. For example, an antenna, software-defined radio, spectrum analyzer, vector network analyzer, VNA, whatever. We're interested in knowing how much voltage passes through port 1 into our device, whatever it may be. If the characteristic impedance of our coax matches our device, most of the energy passes through. To quantify this, we measure S11 using a VNA. If there is an impedance mismatch, part of the wave will reflect. If the surface is conductive, such as a metal, then the entire wave reflects. I will say there are caveats. For example, a solid copper surface will reflect the wave out of phase, while so-called metal materials can reflect in phase. This has implications on electrically small antennas and other applications, but that's way outside the scope of this video. I'm grateful for reflections. Without them, we wouldn't be able to see anything unless we looked directly into the light source. We would all be staring at the sun, going blind just trying to see. We quantify the reflected portion of the voltage wave using the voltage reflection coefficient, which is often represented by the Greek letter gamma. This is the ratio of reflected voltage to incident voltage. It is important to note that the reflection coefficient is a complex value with both magnitude and phase. The magnitude of the reflection coefficient gamma will always range from 0, meaning no reflection, to 1, which means total reflection. S11 is a full complex reflection coefficient. It includes both magnitude and phase information. Return loss, on the other hand, is purely a magnitude. When discussing return loss, we consider only the magnitude of the reflected wave, ignoring phase information present in S11. Let's examine a practical example with a 2.4 GHz Wi-Fi antenna that I designed using ANSYS HFSS. I don't have a good reason for using such a wideband rating element. Perhaps I spent far too many days tuning narrowband antennas in the anechoic chamber. Now let's take a look at the magnitude of S11. The antenna shows an excellent impedance match across a wide frequency range and certainly includes the Wi-Fi band that I am targeting. For this example, we would say that this antenna has an S11 of minus 27.29 dB at 2.4 GHz, or equivalently, we could say that it has a return loss of 27.29 dB. You don't need to explicitly say magnitude of S11 when expressing it in dB, since the dB representation inherently indicates magnitude. A quick side note, and possibly a future video topic, just because the return loss bandwidths look great and datasheets often make impressive claims, it doesn't necessarily indicate consistent gain or favorable radiation patterns across that bandwidth. For example, let's check peak gain versus frequency for our antenna. Around 2 GHz, despite excellent input match, the peak gain significantly drops. Back to the S11. Here we are looking at the magnitude of S11, which itself is a linear ratio, but the dB representation, like minus 27 dB, is the logarithmic form. An antenna S11 of less than minus 10 dB typically indicates acceptable performance, meaning about 1/10 of the power is reflected. For instance, if an antenna isn't properly matched, the reflected energy could travel back into the RF power amplifier. This reflected signal might cause the amplifier to become unstable, leading to oscillations and potentially causing the amplifier to burn out or become damaged. This is why ensuring a low S11 isn't just ideal, it's often critical. For circuit design, you generally aim for even lower S11 values to ensure better impedance matching and minimizing reflections. But for antennas, we're not building pianos. Minus 10 is good. So in closing, what is the difference between S11 and return loss? Simply put, S11 in dB has the opposite sign of return loss. This relationship makes intuitive sense because return loss already implies the negative effect. If you're watching football and your team loses by 3 points, you'd say, "We lost by 3 points," not "We lost by minus 3 points." If you found this helpful, please subscribe. Upcoming videos including antenna designs, radar simulations, direction finding methods, and even exploring metamaterials. Let me know which topics you find interesting in the comments.